This homework solutions video is for Science and Mechanics, Unit 5, Simple Machines, Section 4, Inclined Planes. Number 1. A pallet stacked with bags of cement weighing a total of 300 pounds must be pushed up a 7-foot incline to a platform that is 10 inches high. What force must be applied to get the job done? And here we're going to neglect friction. The first thing that we're going to look at in this problem is to see if our units are consistent. So we have a platform that's 10 inches high, and the horizontal length that we are moving this load is 7 feet. So we need to have the same unit. So we're going to convert our 10 inches into feet. So 10 inches, 10 divided by 12, is approximately equal to 0.833 feet. The next thing that we're going to look at is in this problem, we want to figure out what force must be applied to get this job done. So we're trying to find the effort force needed. And in order to find the effort force, that is equal to our load force divided by the ideal mechanical advantage in this case. Because we're neglecting friction, we need the ideal mechanical advantage, which we do not have. So we have to find the ideal mechanical advantage before we can solve for the effort force. So the ideal mechanical advantage, and we'll do this calculation off to the side, is equal to the horizontal length that the load is moved divided by the vertical height over which it's moved. So the horizontal length will be the length of the incline, which is 7 feet. The vertical height that this load will be moved, we just found to be 0.833 feet. So taking 7 feet divided by 0.833 feet, we get an ideal mechanical advantage of approximately 8.4. So now this ideal mechanical advantage, we can substitute in our equation for the effort force. So our effort force is equal to the load force, which is how much the total load weighs, which is 300 pounds, divided by our ideal mechanical advantage, which we just found to be 8.4. We end up with an effort force of approximately 35.7 pounds that must be applied to this load in order to push it up the 7-foot long incline of a horizontal or vertical length of 10 inches. Number 2, an effort force of 1,200 newtons is applied to a jack screw having a pitch of 3 millimeters and a handle length of 270 millimeters. What is the ideal mechanical advantage of the jack screw? So in this problem, again, we're finding the ideal mechanical advantage because there are so many losses due to friction that it's very difficult to find the actual mechanical advantage. So we're going to find the ideal mechanical advantage, which is 2 times pi times the radius divided by the pitch. So in this problem, as long as the radius and the pitch initially have the same unit, it doesn't matter what unit that is. So our radius will be the length of the handle, which is 270 millimeters, and the pitch is 3 millimeters. So because they each have the same unit, we don't have to convert any of those units. So when we take 2 times pi times 270 millimeters and divide that by the pitch of 3 millimeters, these millimeters cancel out. That's why we don't have to convert their units. And we end up with an ideal mechanical advantage of approximately 565. The next part of the question asks us how much weight can actually be lifted if the efficiency is only 70%. So in this problem, to figure out how much weight can actually be lifted, we first have to figure out how much weight can be lifted, or what's the load force, if we have a mechanical advantage of 565. So the load force is going to equal our effort force multiplied by that ideal mechanical advantage. So the effort force, we're told, is 1,200 newtons, and our ideal mechanical advantage is 565. So the load force that can be lifted is approximately 678,000 newtons. Now, however, we only have an efficiency of 70%, So we need to figure out the actual amount that can be lifted. So that's equal to the idealized load force multiplied by the efficiency. So our load force was 678,000 newtons. The efficiency we're told is 70%. And anytime we are doing any calculations with percents, we have to convert them into decimals first. So 70% becomes 0.70. So the actual load that can be lifted will be 678,000 times 0.7, which is approximately 475,000 newtons, rounding to 3 significant digits.